Okay, so number 5. Uh, the first thing we want to do with even and odd functions is you want to start with the property with the smaller interval. Okay, so we want to don't look at the value here. Look at the interval. So which is a shorter interval? -3 to 6 or from 3 to 0? 3 to 0. So this is where we start. Okay. Mhm. It allows you to see things a little better, especially if there's overlapping things going on. So the shorter interval will kind of help you kind of build your graph a little more clearly. So I always suggest that we start with the shorter interval in case there's an overlap, and there will be an overlap in this case. Now, there's something a little strange about this interval. We typically have the lower bound being what compared to the upper bound? Yeah, lower bound is usually less, right? Now, I said that it doesn't matter if you're working this problem like depth integrals and you're plugging in and solving, but if you're trying to visualize what this looks like, we prefer to have the bounds read from left to right. So, because this -4 is kind of backwards in terms of reading the graph from right to left. So if I want to read the graph from left to right, I can adjust the bounds. But if I adjust the bounds, what adjustment do we have to make? This -4 is turned into a what? A +4. So if I flip the bounds, I'm changing the value, and it makes it a little bit easier, right? Because these are the same things, but this is easier to interpret. This is just going to be a region above the x-axis, and we call it area 4. Okay. So let's start with this smaller, shorter interval. So from 0 to 3, I'm going to create a region. I'm going to call it 4. Now, before we move into the larger interval, let's go ahead and decide what does that even property tell us about the graph. If the function is even, what do I know about the other side, just based off of what I have so far? Same, right? I'm going to create a mirror image on the other side of the y-axis. So I'm also going to create a region called 4 from -3 to 0. Okay, so this is helpful because if I can have this set in stone, then it's a lot easier to interpret what's going on here. Okay, so now from -3 to 6, I want this region to total to be 10. But what I don't want to do is this. I don't want to create a big overlap like this and call it 10, because then you're creating some additional information that you don't need, right? This is already set in stone. We don't want to build off of what we already established, right? We've already established this is not going to change or anything, but we just want to know that everything that is in this region is going to add up to what? Add up to 10. So if I have 4 and 4 sitting here, what's left over that I can fill out to make it 10? 2, right? So from 3 to 6, this must be equal to 2. Now, going back to the even property, if this is 2, what else can I put on the other side? Also 2, from -6 to -3. So now that I have the full graph in front of me, I'm just looking to add what they want me to add. So from -6 to 3, what does that add to 3? 10, yeah. Okay, try part B. Part B, again, the same 3 steps. Start with the shorter interval, then fill out the other side, because if it's odd, what do you know? It's going to be equal, but opposite, right? So whatever you have on one side, you'll get that on the other side. So once you get your shorter interval, then build out the other side, and then once you have those things set in stone, then you can do your larger interval last. All right, so I want you to try that. The key is on the next page. I want to do this before I forget. I want to walk around real quick and have you guys tell me at least the juniors and sophomores, what math course you want to take next year, whether it's BC or stats.
Yeah. Oh. I think you should. Like each individual body of this. I can't go back. Dude, I'm not on it. Oh, there's my piece. Your dad's. This is magenta. One is magenta, one is pink. So it's fine, just fine. Oh.
You got this set. This. Yeah. Now.
I do have to do that after I get back.
And for.
Maybe, dude, that has a.
I still attend that building.
No, but I just.
Yeah, on everybody. Oh, sorry. That's okay. Sorry about that. Okay, hope I got everybody. Okay, so let's go over part B. If the function is odd, find the integral from 0 to 6. Again, same properties. Let's start with the shorter interval. Again, 0 to 3 is 4. But now it's an odd function. Before we fill out the larger interval, let's fill out the property. This is 4. What do you know about the other side? But it's odd function, so it's equal but opposite, so it'll be a -4. Okay, so now we want the interval from -3 to 6 to add up to be 10. Okay, we want everything to add up to be 10, but we don't want to create any more in this region, right? This is already set. So if I have -4 plus 4, what does that equal to? 0. So what still remains? 10. So I need this whole region to be 10 in order to fulfill this property, right? So if this is 10, then what do I know about the other side? This would be -10. Yeah. Okay, so now once we have the graph, everything in front of us, we can add up what they're asking us to add up. From 0 to 6 equals to what? 14. Okay, so if you follow that procedure, shorter interval first, then fill out the other side, and then the larger interval, then you won't get caught trying to figure out, how to fill out the remaining 4 parts. I think if you follow that procedure, things will be a little bit more clear as to where things go. All right, let's go to page 10. Okay, so here we're taking advantage of the properties and seeing if we can use the properties to find the definite integral. Okay, so we know that the region from 3 to 7 is equal to -4. We see part A has those properties as well. Is there anything that I can do to rearrange it to make it match the property from 6 and make a substitution? Yep, I can flip the bounds to match, and I can pull the 2 out. So I'll do 2 things at once here. I'll pull the 2 out. I'll flip the bounds. If I flip the bounds, I need to draw a negative outside. So once I made the adjustment, I'm able to see the piece that I can easily substitute. So this gets replaced with what? -4. And so therefore, -2 times -4 is 8. Okay, next one. Also, I can flip the bounds, but gotta be careful here. The -2 is inside the antiderivative, so we can't just separate the -2 and just treat it like it's independent. It's impacted by that integral. So let me separate first. I'm going to separate first. So I know exactly how that 2 is getting impacted. This I can flip the bounds, and I can use the property. Right, replace this with -4, and negative times -4 is +4. So that's almost done. Now this piece, though, how do we handle this problem? Well, this one, we're not going to use the property. This is actually something that we can solve by hand. What rule can we use for that? What's the antiderivative of 2? 2x, right? So we can do this using power rule. You can flip the bounds if you want, but because we're doing the process for power rule, we don't have to flip the bounds because if we just follow the procedure, it'll work out the same way. But if you want to flip the bounds, you can from 3 to 7 and change that to a plus. But either way, we'll get the same answer. Okay. Yes. Oh, 3, sorry. That 3 needs to be drawn out in front. So let me pull a -3 out of front. Forgot about that. Okay, so here we said integral is 2, so 2 becomes 2x. Evaluate between 7 and 3. Upper bound first, top. So 2 times 3 is 6. Minus 2 times 7 is 14. 6 minus 14 is -8. So let's put it all together here. -3 times -4 minus a -8. All right, so I gotta make sure I keep track of that negative. The antiderivative is -8 from the second integral. The first one is going to be -3 times -4, so 12 plus 8 is 20. Okay, number 7 looks messy, but we know this is definitely going to be a u substitution because this is too messy for any one rule to handle. We can't separate this and say, okay, I'll take care of 2 over x squared, then I'll take care of secant, then I'll take care of tangent. It's all being multiplied, so it's all connected. We have to resolve them all at the same time. It's all part of one problem. Okay, we can't separate. So one thing I noticed is, well, I see a bunch of parentheses here. So is there something that you recognize in terms of, is there a rule that we can try to target towards? So imagine replacing these with u. Does that feel recognizable? Okay. But in terms of what rule do you think we can make this eventually look like? Does this look like this rule? Yes. All right. So if I can somehow work towards this rule, then we have a rule that we can follow, right? What's the integral of secant tangent? Secant. So it's a little bit of, seeing if we can imagine what the problem is kind of headed towards, right? So that kind of gives us a little bit of a head start. If we let the u value be 3 over x, we find the derivative, and we hope that the derivative will take out this 2 over x, or at least take out this x squared that we want to be removed, okay? Because we can't move forward with u substitution unless all the x's are, I found a way to go away. Okay, so we can let our u value be 3 over x. And we want these both to be our u values because we want to make it look like the rule above. And I'll go ahead and underline dx as well because those are our first priorities. We want to find a way to replace those pieces first, and then we'll see where the rest of the problem lands. Okay, so if I want to find the derivative for 3 over x, I would prefer not to go through quotient rule. What can I do to avoid quotient rule? Bring the x up to the top, make it 3x to the -1. Okay, that makes it a little bit easier. I can just go through power rule. So du dx, 3x to the -1 becomes, what's power rule? Yeah, multiply by -1, and then we do it with the exponent. Subtract, right? Yeah, so with power rule for derivatives, we bring the exponent down, subtract 1 from the exponent, so it becomes -2. Okay, let me do some cleanup here. Let me cross multiply, and I'm going to solve for dx so I can make that replacement. All right, so everything that I need to replace, I can do. So I'm going to recopy everything that I see above here. I'm only going to make a replacement for what I've underlined. Okay, did the x's go away? Yes, okay, so we have to get the x to go away. If the x's do not go away, we can't just let it stand to the side and handle it separately. Or we can't ignore it. We can't just let the x squared hang on until the end of the problem. We don't have a rule to follow if the x's don't go away. Okay, so anything that I can push out in front, 2 over -3, right? Okay, so two things we want to make sure that we have. One thing is we should be looking at an easier problem, which we are. And second, we have to make sure that there's a rule that's available for us to use, and there is. Okay. Yes. Oh, sorry. I meant to just make one of them negative. I didn't mean to bring that negative down. Yeah, so just be negative either with the 2 or the 3, but not both. Okay, so it's just -2 over 3. Integral of secant u tangent u. Okay, we said the antiderivative of secant u tangent u is secant. So it's just -2/3 secant u plus c. But u is only a temporary variable. We have to bring what back into our answer? X. Okay, let's try number 8. 5x integral of square root of 2 minus x. Okay, so first thing we always try to do if we see just in terms of x, can we distribute and expand this out and rely on power rule? Okay, we can't. Okay, so this square root terms on the inside prevents us from distributing, right? We can't distribute across multiple terms inside a radical. So, okay, we're stuck in this form. We know we have to go through use substitution. Let's rewrite this problem using parentheses to help us. Okay, so we need to find a u value. What's our u value? 2 minus x. Is this going to cancel out nicely with this 5x? Okay, not quite. Okay, but we're still going to go through the process. We just know that we're going to do a little bit more than just a simple substitution. We got maybe do another set of substitutions. So let's see if we can decide what to do once we get there. So solve, let u equals 2 minus x, du dx is what? That's -1. Okay, cross multiply. So negative dx equals du. I move that -1 over, so dx equals negative du. Okay, make my substitutions. Keep everything except what I've underlined. Okay, what's the problem here? The x is not gone away. I see some students do this. They see this and they say, well, I'll just apply them separately. I'll do power rule here. I'll do power rule here, and I'll end the problem. We can't take the antiderivative unless this x is first resolved. So this x is standing in the way from us moving forward. We got to get that x either canceled out or in terms of u. Is there a way to, we see that's not going to cancel out because there's no x's left in the problem, but is there any way to replace this with something else? Good, solve for x with your equation. All right, so x equals 2 minus u. So this piece is going to go in for this x here. Okay. There's still some algebraic steps ahead of us, but at least we've taken care of the big issue that's preventing us from moving forward. There's a lot of things that I could distribute through, but if I just move things around, I can just work it out so that I only have to distribute one thing through. So I'm going to see the 5, the usual 1/2, and -1. I can kind of just move it all in front, make it one thing. And that way, when I distribute, I want it to do pieces at a time. Right, this feels a little bit cleaner if I have it in this form, because I can just distribute the negative, the 5, and use the 1/2 all at once. So we still can't do power rule yet, but we're getting close. Once I distribute that through, I should be ready to go for power rule. So what's negative 5 u to the 1/2 times 2? Negative 10 u to the 1/2 plus 5 u to the 3/2, right? 1 plus 1/2 is 3/2. Right, so now everything is nice and clean. We can now do power rule. Flip those fractions to merge with the coefficients that you see in front. Okay, we've done a lot of work, and can we leave this as our answer? One more thing to do is to do it. Yeah, substitute the u back with x. So I think for some reason, these are the types of problems that, especially with change of variable, the second set of substitution where students tend to leave their answer most in terms of u. I see students, they do fine bringing the x back in other problems, but for this problem, tend to leave the u. So just keep in mind, for every answer, we should never have our answer in terms of u. We should always bring it back to the original variable. Okay. Any questions with 8? Okay, let's go to 9. Okay. Okay. So what do we not do first? The bounds, right? The bounds is not going to involve this expression at all, right? So if you want, whenever you see bounds, just pretend like you don't see the bounds. We got to solve this problem before the bounds can be used. Okay, so if you look at this problem here, is this possible using just power rule? Yes, yeah, there's only one term below. We recognize this form from the quiz. This is easy enough for us to split up and separate. Nothing is preventing us from moving forward. If you try to go through U substitution, it's not going to work. Okay, so that's why I keep stressing that we got to make sure if a problem is meant for expansion power rule, we got to use that method, because if we don't, it's not like a U substitution can catch all the different types of problems. Okay, some problems are not meant for that process and it won't work that way. Right, so let's clean up. I'm going to go ahead and rewrite that square root of x as x to the 1/2 and start splitting up. Bring the denominators up to the top, change their signs. Add exponents, 1 minus 1/2 is 1/2. Okay, go through power rule. Okay, do we put a plus c here? Why not? Because we have bounds. Okay, so we're going to clean this up, and then we can work in the bounds. So now we're ready for the bounds, right? So the bounds is never going to be used with what you see in front of you. It's going to have to deal with the transformed expression that you handle. Okay, now that 9 and 4 can be used. Top bound first. Minus parentheses. Okay, I want us to practice reducing these values by hand. And I know you're looking at this thinking this feels like it's difficult to do, right? 9 cubed and then taking the square roots, that seems hard to do without a calculator. So my suggestion is don't do the cube first, do the square root first, right? We don't have to do the 3 before the 2. We can handle the 2 first. So what's the square root of 9? 3. So then 2/3 times 3 cubed becomes a lot more manageable, right? 9 cubed is a really large number, and then taking the square root feels a lot more difficult. Why don't we break this number down to a smaller one and then raise it to a power? That feels much easier. Okay. What's square root of 9? 3. 4 cubed, that's a large number. Why don't we break it down first? What's square root of 4? 2, and then 2 cubed is much easier. Distribute the negative through. Again, okay, careful, we can't do this. We can't do 2 times 4 and take the square root, right? So the radical has to take priority before multiplication. Okay, so square root of 4 is 2, then multiply by the 2. So 2/3 times 27 plus 6 minus 16/3 minus 4. Okay, I do want to talk about how if this is non-calculator, you can leave your answer in any of these forms. Okay, but I want to make sure that we understand how to break a number down if you wanted to break it down without a calculator. Okay, number 10. We see a definite integral, but the bounds is the last thing to be handled. So we can just basically pretend like we don't see the bounds and approach this problem first. Okay, tangent squared, secant squared, we don't have a rule that can handle this. We can't say, oh, this is just same thing as secant tangent, and then I can just square everything. Okay, if it doesn't look exactly like the rule that we have, we can't manipulate the rule and adjust anything. Okay, so these rules are very strict, right? So if it doesn't match exactly, we don't have a rule to use. So we got to go through U substitution. But it's hard to maybe see what the U value is. So maybe let's create a set of parentheses. Oh, and also I just thought of this talking with the previous with other periods, is when you go through U substitution, you're never going to do this. Okay, you're never going to replace just the X with U. The reason why is because the whole purpose of U substitution is to make your problem much easier to work with, right? If it looks almost the same, but with just one variable change, you haven't made any progress. So U substitution is not going to have any benefit for you if you're just making one variable change. Your U value is always going to be a usually a significant portion of the problem, much larger than just a straight one-to-one replacement. Okay, so yeah, if you go with the U substitution, you're never going to just do this. It's always going to be more than just an x. Okay, so if I rewrite this problem here using a set of parentheses, at least I have some options to choose from. Because our u value can be either tangent or secant, but not both. So if we let our u value be secant, if we think ahead, the derivative of secant is what? Secant tangent. Is secant tangent going to pair up nicely with the remaining parts of the problem? Right. It's not a good fit, right? What if the u value was tangent? The derivative is secant squared, and we see that, okay, if the derivative matches nicely with the remaining part of the problem, you know that you're going along the right path. Okay, so that's going to be our u value. Okay, so u equals tangent x. Okay, we make our substitutions, u squared, secant squared, du over secant squared x. All right, do the x's go away? Yes, so that's a good sign. Okay, your problem will always look much easier and cleaner than what you started with, and we should be able to recognize this as a rule that we have available to use. Okay, so right now, we only have 7 rules that we are working with, right? You got power rule, and you have your 6 antiderivative trig rules. Okay, if it doesn't look like one of those 7, we don't have a rule to use. Okay, so u squared becomes u cubed over 3. Okay, can I just do half bracket and plug in pi over 3 and 0? Okay, not yet. What's the issue here? Why can I not do this with 0 and pi over 3? Not the same variable. Okay, so these are in terms of x, but this is in terms of u. So either we convert the bounds using the u equals tangent x, or you bring this back in terms of x and then plug in the original bounds. Okay, so I'll work it both ways. I think most students prefer bringing in terms of x and just use the original bounds. That's perfectly fine. So we can work it that way. So u cubed over 3. Let's bring the original variable back, bring back tangents. And then we can work the bounds pi over 3 and 0. Okay, so if you think about your unit circle value, tangent of pi over 3, the order pair is 1/2 root 3 over 2. So sine over cosine, y over x is just root 3 over 1. So I have root 3 cubed over 3 minus 0. Tangent of 0 is just 0. So square root of 3 cubed is just root 3 times root 3 times root 3. So that's just going to be 3 root 3 over 3, which is equal to just root 3. Okay, so most students prefer this method, which is great, which is fine. But I do want to work the other method. Now, on the test, you can choose either method. I'm not going to have you try to do both at the same time. You choose which one you want to do. But the other way you can do it is you can leave this u cubed over 3 alone and then play with the bounds instead. So we can convert the bounds. If x equals 0, then u equals tangent of x. Therefore, u equals tangent of 0, which is 0. Right? So our new lower bound is still 0, okay? And then if x is equal to pi over 3, then u is tangent of pi over 3, which is equal to root 3. Okay. Then we can use those bounds with the u bounds with the antiderivative in terms of u. Feels a little bit cleaner because you've done the heavy work ahead of time. So plug that root 3 in, we get root 3 cubed over 3 minus 0 cubed over 3. Same result, right? Square root of 3 cubed is 3 root 3, 3 root 3 over 3 is same thing as root 3. Okay, so you can choose either method. What you don't want to do is you don't want to use the u antiderivative with the x bounds. Okay, so we don't want to plug in pi over 3 and 0 in for that. That's not correct. Okay, a few minutes here. Let's see if we can do 1 or 2 problems. Page 13. Actually, I do need to show you one type of problem on page 14, and that is absolute value problem. So with absolute value, we're not going to do power rule. We're not going to try to figure out power rule for this. The easiest way to go is to draw the graph. Okay. Now, do you know what an absolute value graph looks like? What's the shape of absolute value graph? Looks like a V, right? So absolute value of x looks like this. Okay. So what we can do is we can just start off by drawing this graph. Okay, let's draw this graph. Now, absolute value of x plus 2 means that you're going to take this graph and you're going to shift it which direction? But it's opposite. It's going to be left. Yeah, so left 2 units. So this is what the graph looks like. Okay, doesn't matter. Don't have to worry about what to make the slope of the graph, but you just make a V out of it. Okay, so we want to go from -5 to 6. So go ahead and count the graph to -5, 3, 4, 5. Okay, to 6. 1, 2, 3, 4, 5, 6. And extend the graph as you see fit. Now, what shapes do you see between the graph and the x-axis? How many triangles? 2 triangles. So really, antiderivative is really just the area. Everything's above the x-axis. So if I find the areas of these 2 triangles, I have the antiderivative here. So if I plug -5 into the function, I can get the y value. So what's -5 plus 2? -3. What's the absolute value of -3? 3. So we know the y value is 3. So put the order pair there, -5, 3. Okay. To find the height of this triangle here, plug 6 into the absolute value function. What's 6 plus 2? 8. Absolute value of 8 is still 8. So order pair is 6, 8. So let's do area is 1/2 base times height. So what's the width of my first triangle here? 3. And the height of this triangle is also 3. Okay. What's the width of my second triangle? 8. What's the height of my second triangle? 8. So 1/2 base times height is the area of my first triangle. 1/2 8 times 8 is the area of my second triangle. 9/2 plus 64/2 equals 73/2. So if you see absolute value, treat it like a geometric problem. Draw the graph. It's always a V shape. Drop the drop the vertical line, find the y values at the endpoints by using the absolute value function, convert everything to be positive if there's still a negative, and then 1/2 base times height plus 1/2 base times height. You're just adding two triangles together. Okay. I'm gonna have a help session this afternoon, and also tomorrow morning at 7:30, and then Friday, 7:15. I'll continue to pick problems. Tomorrow in class, we'll work through this. We didn't get to the calculator stuff, but it's okay. Our focus is trying to get ready for Friday. We can fill in the other stuff next week. All right, don't forget your phones.
Oh my God, you see the. Yes. Yes. I gave the,
Give it to me, so I'll just throw me there.
Okay, on the test, are we gonna have to be able to do like the particle motion, like the graph?
Yes, not for next week.
Okay.
Yeah, so,
Just what's on
yeah, if you look at page 13, 14, that's a very good representation of what you're gonna see on.
13, 14, got
Yeah.
it.
No, the, yeah.